So today what we're going to do is we're going to start, or we're going to finish up what we had been doing, which is figuring out how to calculate the Fourier coefficients for each of the forms of the Fourier series. We're going to assemble the series, meaning I'm actually going to use the individual components to build the waveform. And then we're going to talk this today and next week about how you actually calculate the values for an arbitrary waveform. It's like I was showing you for a square wave, right? Somehow I knew that the coefficients were 4 over pi and 4 over 3 pi. Well, I didn't just know that, right? There's a way of calculating it. So we're going to go through how to do that. All right. So what have we kind of gone over, basically? Just kind of recapping a little bit. So starting last week, we talked about this notion of the 4 ways to approach the sine wave. All right. We started this on Tuesday. We went into it on Thursday again. So if you're trying to figure out how to review for the exam, or for the homework, you probably want to take a look at the end of that lecture when you're dealing with problems associated with this stuff. Now, basically what we're saying is there's 4 ways to think of any given cosine wave. And I said, normally I think of it this way from a circuits perspective or a differential equations perspective, because you say if I put a cosine or a sine wave into a system, like a circuit or any kind of system that's described by differential equations, what can happen to that cosine wave? Well, it can get scaled, that's the phi, and it can get shifted bigger or smaller, that's the amplitude piece. All right, so only 2 things can change, the amplitude and the phase shift. The frequency never changes. Now, we spend an inordinate amount of time talking about this stuff, it seems like, right? And the reason we do is because most of the waveforms that we deal with, that we analyze in engineering systems, oftentimes are cosines and sines, or they can be represented as a Fourier series, meaning that they're sums of sines and cosines. All right, so we got 4 ways of trying to represent this thing, right? So I've got this first approach here, right? I've got this guy, which is a sum of a sine and a cosine. And then I have this approach that's 2 rotating vectors. And then I say it's the real part of some rotating vector, which I call the dynamic phasor. All right, so basically I've got 4 different ways to represent this thing. So just to make sure that this makes sense, so what I wanted to do is just kind of do a quick example. We did this early on in the semester, but it gets a little bit, it's hard to maybe wrap your head around this at the beginning of the semester. All right, so now we're going to come back to it. So in this case, what I have is an example. Let's call this guy my x of t. All right, what I plotted here is 6 cosine omega t plus 45 degrees. And my omega in particular was this guy, all right? 2 pi over 0.01. What's the period? Mm-hmm. 0.01. Yep, right? Because 2 pi over t is omega, right? And you can kind of see that too from looking at the graph. It goes from 0 to 0.01, right? All right, so I plotted 1 period of that thing. All right. So what I did here was I said, okay, this is approach number 1. What I'm also showing here is approach number 2 and approach number 4. Now, what I'm trying to say is that what is supposed to be true is that, all right, x of t, 6 cosine omega t plus 45 degrees is equal to 3 angle 45 degrees e to the j omega t plus 3 angle negative 45 degrees e to the negative j omega t, and the real part of 6 angle 45 degrees e to the j omega t. That's what I'm saying here. All 3 of those things are equal. So for approach 2 down here, there's 2 vectors that I drew. All right. What are the 2 vectors that I drew? What are the 2 vectors that I drew? There's one here and one there. What are those? So this is the approach number 2. So this is the complex plane. So this is the real, and this is the imaginary. Real, imaginary. What have I drawn there? Well, first thing I drew is I drew this, right? 6 angle 45 degrees e to the j omega t. First of all, e to the j omega t, that messes you guys up, right? Look at that. E to the j omega t is basically a vector with a unit magnitude and an angle of omega t. Okay. So in other words, I can think of this thing as 6 angle 45 degrees times 1 angle omega t. Right? That's what that is. All right. At what time did I draw this vector? What t value is that vector? First of all, if I multiply two vectors together, 6 angle 45, 1 angle omega t, what's the magnitude of that sum? 6, right? What's the angle of that sum? Omega t plus 45 degrees. Okay. Omega t plus 45 degrees. This is I mean, you can't tell that. That's a 45-degree angle. So what time did I draw this? T equal to 0. Okay. So at t equal to 0, this guy here is what I call the dynamic phasor. It's this. It's not the static phasor. The static phasor is this, 6 angle 45 degrees. What have I drawn here? That's a good guess, right? But what is the real connection? The real part of that vector, right? So a vector has a real part and imaginary part. The real part is basically, it's the x component of that vector. That's the x component of the vector. So if I look at this at time t equal to 0, remember these vectors, both this vector and those two up there, rotate as time advances, right? In order to make this true, those vectors rotate. So at time t equal to 0, all right, if I look at my original x of t, so at time t equal to 0, I drew a big blue dot right there. T equal to 0, at this time, x of t is equal to that. So in other words, I plugged in t equal to 0 with that frequency, and I got 4.2426. Okay. If I go into the other two, so if I plugged in for approach number 2 here, right, at t equal to 0, this guy also, the real part of that vector is 4.2426. In other words, this length right here is 4.2426. The real part of that vector has that length at that time. Okay. Now, it's not obvious, but what we talked about is if I look at this vector plus this vector, what happens to their imaginary parts? Let's look at the picture here. All right. This is at time t equal to 0. This is one of the two vectors up here. This is the other one. What's true about their imaginary parts? Well, yeah, so those two vectors are conjugates of each other. If I add two conjugates, what happens to their imaginary part? They cancel out, right? And you can see that here because this guy's imaginary part goes up, his goes down by the same amount. So there's no imaginary part left. The sum is entirely real. And the sum of those two, if it's entirely real, means it's going to be on the real axis. So the length of this part is 4.2426. All right? This is the real, this is the imaginary. Now let's say I choose this time, t equal to 0.0013 seconds. All right, so if I plug that in there, what I find is that at that particular time, the cosine function is equal to 0. Okay, cosine function is equal to 0. So what does that mean? So if the cosine function is equal to 0, what that does is I plug in the values here. So if I plug in these values, to make sure you guys understand, okay, so if I plug in this value of t, what ends up happening? Well, omega t, if I plug in those values in this particular case, omega t is going to equal 45 degrees. Okay. Omega t is 45 degrees. So if that's the case, where does this vector sit? E to the j omega t messes with your head. E to the j omega t is length 1 angle omega t, right? Length 1 angle omega t. So if I have 3 angle 45 times 1 angle 45, what is that product? 90 degrees. 3 angle 90 degrees, all right? And so that is here. Okay. This guy, the other one, is here. Where's the sum of those two things? I got one vector straight up, one straight down. What's the sum of those two things? 0, right? There is no real part. That's exactly what we would expect. The sum is right there. Exactly what we would expect it to be. Okay. For this guy here, again, we just said omega t is 45 degrees. So that means that we're taking the real part of 6 angle 45 degrees times 1 angle 45 degrees. If I take 6 angle 45 times 1 angle 45, what's that? Six angle 45 times 1 angle 45, what is that? 6 angle 90, exactly, right? So if I look at that, he's pointing, so here he is right here. He's pointing straight up, right? He's bigger than my axis. Does he have a real part? If I have a vector pointing straight up, I take the real part of this vector, right? I take the real part of that vector. What is the real part of the vector that points vertically up? 0, right? So it's following that. The thing to think of is what's happening over time with these approach 2 and approach 4 is that those vectors are rotating around in the complex plane. But they always equal to whatever the value is at the same time on the original waveform. That's where the equality comes in. Now, the reason, like some level, it's like, well, why are we worried about this? Why we worry about this in part is for a couple of reasons. One is the calculus gets a lot easier. Primary reason we use this approach is what you'll see in circuits 2 is when I'm talking about steady state conditions, I can either use differential equations or I can use impedances. This allows me to use impedances, which is way simpler than deal. So it's way simpler mathematically to deal with that stuff than it is to deal with this stuff. All right. Than it is to deal with the time domain waveforms. All right. So you'll see that a lot more. All right. So we went through that. The concepts you guys should be, honestly, you should be pretty comfortable with that stuff by now. If you're not, you need to get there. This stuff is all new, though. I'm talking about Fourier series. All right, so we introduced this idea, the fact that I've got 3 different ways to express any periodic waveform, okay? Any general periodic waveform. Either I can use what I call the sine cosine version, where I add a cosine and a sine at the same frequency, a shifted cosine, or a complex form. Now, this summation, we've talked about how to think about the summation. In this form of the series, in the top form of the series, I go from n equal 1 to infinity. In this one, I go from negative infinity to infinity. Why? Why does this one have 2 times as many values as that? Why does this form have twice as many values as that? Because I have to have the counterclockwise and the clockwise. All right. So I have to have 2 e to the j n omega naught t. So these n values here, what I see is n is always multiplying the frequency. What did I call omega naught? Which is 2 pi f naught. What do I call that? Fundamental frequency. And I called n the harmonic number. I say these frequencies are harmonically related to each other, meaning that they're all integer multiples of fundamental or base frequency. Right? So we had a couple of core definitions. So we said we had our fundamental period. All right, smallest, need to be careful of this. The smallest frequency, it's the largest period. Right? Largest period over which the waveform repeats, or smallest frequency. Okay. Fundamental frequency, 1 over T naught. Harmonic number n, the harmonic frequency n times f naught. And then I said our DC term has a frequency of 0, right? F equals 0 times f naught. So n equals 0. So f equals 0 times the fundamental frequency, or 0 hertz. 0 hertz basically is a constant, right? This guy, the DC term, is always the average value of the waveform. All right, and we're gonna do some more calculation examples with that today. All right. So the example that I went through in detail the other day, I want to finish up with it. What I talked about the other day is I went through A, B, and C. So we figured out the fundamental period. We determined the highest harmonic frequency in this guy. And then we calculated the A, B, C, phi, and alpha values. Now, what I'm going to do, I'm going to talk about this part a little bit again. All right. But then I want to talk about this last part. How do I actually sketch this thing? In other words, what I want to do when I say sketch it, what I want to do is I want to say, all right, this particular waveform here, I see that this guy, first of all, S of t as I've written it there. Let's just make sure. Which form of the series is this one? So I have a cosine with no phase shift, a sine with no phase shift, a sine with no phase shift. Yeah, it's that sum of sine cosine version, right? Where there's no shifts at all. All right, so I see that it has that form. So in other words, I see that this guy specifically has the form A naught over 2 plus this summation from n equal 1 to infinity an cosine n omega naught t plus bn sine n omega naught t. Now, what we did, that's the basic form of it. Now, what that says is I can have an infinite number of harmonics that are needed to create S of t. This guy doesn't have an infinite number of harmonics. He doesn't have to have it. In general, you could have an infinite number. This guy does not have an infinite number. In fact, what we found out is he has a DC term, which is what? Which one's the DC term? This is the DC. This is the constant. And we found that this was the fourth harmonic. This was the sixth. And this was the seventh. So does he have a fundamental term? No, doesn't have a fundamental. There's not a fundamental sine wave that's in this. However, if I plot them all together, what we said is we figured out that the fundamental was 250 hertz. Okay. How did I find that? What's the picture I'm drawing here? How did I use this picture to figure out that the fundamental was 250 hertz? What am I doing in this picture here? Well, I plotted the function. This is S of t. Why did I go from there to there? Yeah, basically the period is the length of time it takes for the thing to repeat. So what I said was, well, the definition of a periodic waveform is one that meets this definition. And I looked at this and I said, well, this guy, it looks like the largest frequency over which this guy repeats is that right there, right? So it's 4 milliseconds or 250 hertz. Now, the other thing that I did was if you know these frequencies here, you can take the greatest common divisor of all of them. All right, that's another way to do it. All right, and I figured out if I run this GCD command in MATLAB, it works out to be 250 hertz. Okay, so we went through this the other day, and I basically looked at this and said, well, because this guy is in that sine cosine version of the series, I went through from n equals 0 to n equals 7. And I said, what's the amplitude of each of the cosines and sines in that series? Okay, so looking at the DC term is 10. If I pattern match to the series, I see that 10 is equal to A naught over 2, so A naught has to be 20. Weird that it has the over 2, but it does. I didn't choose the definition. All right. If I look at this, because there is no fundamental second harmonic or third harmonic, all those amplitudes are 0. Tell me why for the fourth harmonic, meaning 1000 hertz, why do I say A4 is equal to 50 and B4 equals 0? Why did I come up with that? Because I have a cosine, but I don't have a sine, right? So for the sixth harmonic, which is 1500 hertz, I said that B6 was equal to 2 and A6 was equal to 0. Why did I say that? Don't have a cosine, but I have a sine, right? And then similarly for the seventh harmonic, right? I have a sine and not a cosine. So, you know, for what I do, a couple of things here. So when I wrote my code, you can get fancy with code, right? You don't have to get fancy with code. All the stuff and this is, you guys are going to look at my slides, you're going to look at my lecture, and you're going to try to copy what I did. You don't have to, okay? If you're not comfortable with it, what I ask you for in the homework is I say, give me all of the AN and BN values that are relevant, right? So problem 2 and problem 3 are like this. So when I look at this, what I did here is I just created 2 vectors. You can make for loops and stuff like that, but I just loaded this guy up and said, this is my n equals 0 values. This is my n equal 1 values. This guy here is n equal to 7. Now, one of the things that I asked you for here, and I asked you for it, this is exactly like the way the homework problem 2 and 3 is set up. All right, what's n sub d, the number of the highest harmonic frequency? Right, if the signal has 10 harmonic frequencies, then n sub d is 10. For this guy I've got here, what is n sub d? What's the highest harmonic I have in here? 7. All right, so this guy, that's n sub d. Okay. Now, what am I doing here? What's that? What's happening there? And you don't have to run that code if you don't want to. I would. It's finding the magnitude and the angle. So it's using the result that I gave you here is that for any frequency, right? If I know my A and B values, I can use that relationship right there to figure out what those values are. That's what I did, right? I use those, I know A and B values. If I know A and B values, I can calculate the C and the angle, right? Now, what am I doing here when I have this? Explain this line of code to me right here. Why did I do what I did there? Now, to be clear, what you could have done is you could have done C sub n by calculating from n equals 0 to n equals 7. You could have calculated by hand, right? Or with some separate line of code, you could have calculated, you know, so for n, so let's go to n equal to 4, which is here. All right, this guy is n equal to 4. For n equal 4, what I could have done was I could have said, well, C4 is equal to A4 squared plus B4 squared, which would be square root of 50 squared, or 50. All right. But I didn't. Right? What did I do? In other words, I could then load that into the 4th spot there in C sub n. Right? But what did I do instead? What's that? What is that line of code that I have there? That 3rd line.
You perform the element operations.
Yeah, I did element by element operations. So A dot n squared, or A underscore n dot squared, right? What that does is it calculates 20. So it does 20 squared, 0 squared, 0 squared, 0 squared, 50 squared, 0 squared, 0 squared, 0 squared. B sub n would do the same thing. And then take the square root of every entry in that vector, right? And if I look at that, that vector is going to have 8 entries, just like A and B do. Why did I say 8 entries? Doesn't it have 7? Right, because I go from 0 to 7. 0 to 7 is going to be 8 values. Okay. All right. And then I did a similar thing with the angle. All right. I don't have any dots in there, though, do I? Why didn't I do any dots there? There's no element-wise operations, right? I'm basically taking AN minus J times BN. That's not an element-wise operation, right? If I take one vector minus another vector, it's going to do that operation element-wise naturally, right? You learned that in matrix stuff, in linear algebra. Sure. All right. So the code that I have looks like this, all right? there's my GCD stuff that I talked about. This would be very similar to the code that you would need for problem 2, problem 3. All right, so just to understand how I move between the different forms of the series, right? I just want to look at this real quick, just by hand. When I look at this, all right, so we knew that this series was in the form of that sine cosine version of it. All right, so let's look at the sixth harmonic guy right there, right? 2 sine 2 pi 1500t. Okay, so that means that here I have 2 sine 2 pi 1500t. I start with this form of the series. So I figured out that A, in particular, if I'm doing this for the sixth harmonic, A6 equals 0, B6 equals 2. Okay. Now, what I can do is then use these formulas here, plug in the values of A and B to figure out what? So figure out that this is 2 cosine omega t. Now, what should the phi value be? Let's figure if we can figure that out. It says it's the angle of A minus JB. Okay. So angle of A minus JB. So let's think about that. What's A and what's B in this particular case? 0 and 2. So what's the angle of 0 minus J2? And you can do that without a calculator. That's 0. Not 180. You're guessing wildly now. 270. How'd you get 270? It's pointing straight down, right? It only has an imaginary part, and that imaginary part's negative. So that means he's pointing straight down. Those angles 270 or negative 90. All right. So normally we end up saying that's negative 90. Okay. So this guy is that. Okay. Now, to get to the alpha values in this form of the series, what I know is that alpha is C over 2, and the angle of alpha, right, is the same as the angle of phi. So looking at this, I see that alpha 1 has to be what? So I see that C6 equals 2, phi 6 equals negative 90. So help me out to figure out alpha 6. All right, so we know these values. I can then use this, right? How do I figure out alpha 6? If C6 is 2, phi 6 is negative 90, how do I figure out alpha 6? 6 over 2, yep. 3, and what's the angle? Yeah, so I'll say 3 angle negative 90, or 3 e to the negative j90, like so. All right. What's alpha minus 6? Yep, the conjugate of that. A6 conjugate, or 3 angle 90 degrees. So I could do this operation in each individual frequency, but what I do is I code it. All right. So here's all the values. I wrote in all the values there. Now, what I did was I have my frequencies now going from -7 to 7. Right? So I have some negative frequencies. Then I have my A values, my B values, my C values, my phi values, and my alpha values. Now, from -1 to -7 for A, B, C, and phi, I wrote not applicable. Why is that? Yeah, they don't exist in those forms of the series. I don't need them. They only exist for the positive integers, right? In those forms of the series. All right. But I have to include, for every positive frequency here, I have to have the corresponding negative frequency when I have the complex form of the series. All right. So how would I write some code to load these in? Again, you could load them in by hand, but I want to write code to automate the loading in of the A and B values. Well, in this case, I have to load in the A and B values. Once I have those, though, I can automate the generation of the other ones. So let's look at what I did. Okay. So I made a vector little n which goes from 0 to 1 to n sub d. And then I made an n complex vector, which goes from negative n sub d to n sub d. So let's start with this guy first, little n. How many entries are there going to be in that? And we said n sub d was 7. 8. We have 0, 1, 2, 3, 4, 5, 6, 7. Okay, that's 8 entries. What about this guy? N complex. What am I doing here? This guy is going to have 15 entries. He's going to go from -7 in steps of 1 up to 7. Okay, now why did I do that? Well, because n complex is going to run from -7 to 7, and n is going to run from 0 to 7. Now, what I have here is a for loop that I wrote. Okay. Well, before I do the for loop, let's see. What I did was here, I created an alpha vector, which is, so alpha n equals 0's size of n complex. So what's alpha n going to have once I create it? What's it going to contain? What's going to be in the n complex vector? Yep. It's going to be a row vector full of zeros, right? It's going to have 15 entries, going to have the same size as n complex. So then I basically loop through all of the entries in that vector. Okay. Now, what did I do here? Well, this is, again, you don't need to do something like this. I was trying to show you how I might start to think about this. Basically what I did was I said, well, if n equals -7, put in a value. If n equals -6, put in a value. -4, 0, 4, 6, and 7. Why did I only have values there? So I had values from -7, -6, -4, 0, 4, 6, 7. Why did I do it though? Why only those ones did I put in values? All the other values are 0, right? Now, that is a little, you could have just sat there and you could have made an alpha vector and done that. The thing that's goofy about this to me is if I had a 15 entry alpha vector and you were like, well, this one's -10 and this one's, it gets long and confusing. To me, this is a more organized way for me to think about it, right? Which is why I did it the way that I did, right? Now, when I say something like alpha n, so for n equals -7, I did this. What I'm writing there is the number 10 angle 90, right? 20 over 2 is 10. Exponential j pi over 2 is angle 90, right? So I'm basically putting in the full complex value of alpha. Yes, sir.
If you're going to directly assign the values of alpha, why not just assign them to the vector? So like, why put this notation inside the for loop?
Why not just make the vector? So in other words, like if I did, yeah. So the reason why is because it, to me, crap. Oh boy, there we go. I can't write in that corner. Alpha n, because it would end up being this 10 times exponential j pi over 2, and then 1. So I'm gonna write 15 separate numbers if I do that. My small brain has trouble keeping track of that on the screen. I can follow that. I mean, you look at that, that's crazy else if it is sort of, right? But my brain can look at this and say, I can look at that table and I know that for n equal -7, I have this. For n equal -6, I have that. For n equal -4, I have that. That's easier for me to track than counting out. Is that the third 0 or the fourth? I can't.
Like you only need to assign.
You only need to assign a few values, but you would need to create a 15 entry vector. I see what you're saying. You could say
Like,
alpha of 1 equals this.
Yeah,
Alpha,
yeah.
you could do that. The reason why, okay, I'll tell you why I didn't do that. Because when n equals -7, it's the first entry in the vector. When n equals -6, it's the second. So then you have to have this mapping in your head between which entry in the vector and which one. This actually lets me go, well, if n is equal to -7,
Yeah,
this.
it's definitely easier with you.
It is much easier mentally to process, right? My thing is, I thought about this, right? I have some context for it, so that's why I did it the way that I did it. You guys don't have context. That's exactly what I probably would have done when I was a sophomore, right? And I'd be sitting there forever and banging my head against the wall, right? So this is a handy way to do it. You can totally do it your way, the brute force way, right? But brute force is a natural place to start. It's just uglier, right? Harder to track in my head. All right. Now the last part is I ask you to use those coefficients to create the series. What that means is I want to create those summations. Okay. How would I create those summations? Let's start with the first form of the series. So the sine cosine, but how would I create a graph of the actual function? Well, I got to implement that summation. How would I do that? How would you do that? Well, I'm making a time domain thing. So what's one thing I got to do? Got to make a time vector, right? Right, I got to make a time vector. I don't remember. Let's see. Okay. I'll do it here. So I got to make a time vector. Let's do it here. Okay, make a time vector. And I'm going to run it from -2t to 2t. And I don't remember what size steps I did. All right. For whatever reason, I did t over 10,000. I think I know why I did that. All right. So I made a time vector. Got to make a time vector because these are time domain functions. Right? Okay. All right. So how would you create this series? I'm saying I would use a for loop. Okay. So my for loop, and I have an n vector. My n vector goes from 0 in steps of 1 up to 7, or what I was calling n sub d. Okay, and n sub d is 7. Now I'd write a for loop that goes, bless you, k equal 1 to 1 to length of n. Length of n. Right? End it. Now, what would I do here? First time I go into that for loop, k is equal to 1. Right? So n of k would be what? What is n of k? When k equals 1, first time I go into that loop, what's n of k? What's n of 1? What's the first entry? 0. All right, that's the DC term. The DC term of my series was 10. All right. In particular, it was so 10. So what would I do? I would somewhere outside of this, I'd have to create a vector x. Or I guess I'm calling this, let's call it x. Okay. I would create a vector x and I would make it all zeros initially. Right? And what size should it have? Well, it should have the same size as the t vector, right? 0 size t. I always start out with a empty vector. So, all right. Basically what I'm saying is when I go through this initially, first time I go through this, I'm dealing with n equals 0. Okay? When n equals 0, for that frequency, this thing has a value of 10. Okay? So, how do I make that? How do I make a constant 10? How do I include that? How would I include that? Make sure I'm writing this consistent with the way I did this. All right. The way I did this is I said, well, if n of k equals 0. All right, if n of k equals 0, what is that? So if n of k equals 0, right? If n of k equals 0, that's my way of figuring out am I at the DC term? Okay. What I'm saying is X is the summation of, so every time I run through this, I add in another harmonic. So the first time I go through it, I say, all right, well, I want X to be equal to whatever it currently is, a bunch of zeros, plus whatever that constant is supposed to be. All right. So what would that be? What did I do? There we go. What would I do? I would add to X what? I would add 10 to it, right? So specifically what I would do is I would add to it A, because I have the A vector, I would add to it A sub n of 1, which is the first entry in that vector, divided by 2. That adds in this term, all right? And I'm done, all right? For any other value, what would I do? Well, I take whatever X currently is, and I add to it the next entry. Because remember, that's what the summation does. When n equals 1, you add in all the terms for n equal 1. When n equals 2, you add in all the terms for n equals 2. When n equals 3, you add in all the terms for n equals 3. So what would I put in here? I'd have to implement that, right? So in theory, when n equals 1, what you want to do is you want to take the function and you want to implement what this series says. You want to add to it A1 cosine omega naught t plus B1 sine omega naught t. Right? What do I want to do when n equals 2? Yep. I take my current x and I add to it A2 cosine 2 omega naught t plus B2 sine 2 omega naught t. Again, you don't have to use a for loop. You could do it by hand like this. You can just write it out sequentially. Right? Here's how I did this in my code here. I created 3, and I asked you to do this too. I asked you to create 3 versions of the series. X1 is the shifted cosine, X2 is the sine cosine, X3 is the complex. So I created 3 series. Each one of them goes from negative 2t to 2t. How many periods is that? 4 periods, right? And so negative 2t to 2t would be 4 periods. And to be honest, so x1 and x, so this is the DC piece. This is for n equal 1, n equal 2, n equal 3, n equal 4, so on and so forth, right? I go into this else anytime the n value is not 0, right? So I just keep adding to it, and I just basically use the values in the equations there. I'm just basically implementing these 2 equations. I'm implementing the summation in each of those 2 equations. All right, now, a couple of things here. What did I do? I know this. I don't technically have to multiply this by 1s. If I take a vector of zeros and I add to it 10, all of the entries in that vector are 10. I don't think I need to do that, but you can. All right. So you guys follow the basic idea there? All right. In the middle of the night when you're working on your homework, you won't, but it might seem like it makes sense now. All right. If you follow this approach, right, basically this is getting out how I would implement a series in code. Now I did 2 of this series. I didn't do the other one. Right? Why didn't I do the other one? I could have, right? But I only would have been doing half of the series, right? If I did it this way. Why am I saying I would only be doing half of the series? Here, I'm looping through the vector n, and I'm looping from n equals 0 to 7. What do I have to do for the complex form of the series? Negative 7 to 7. That's why I didn't do it here. I made a separate for loop for that guy. All right. This is the for loop I did for that guy. Right? I looped through that n complex vector. All right. And I just have essentially 2 statements, right? What's the first one? If n complex of k equals 0. That means if the n value is 0. Remember, I made two vectors, n and n complex. N went from 0 in steps of 1 to 7. N complex went from -7 in steps of 1 to 7. Now you could, again, this is one of those things, you could have made one n vector that went from -7 to 7, and you could have thought carefully about using only half of them for the other two versions of the series. In my mind, again, that would be a mess to bookkeep. All right. This, again, this is one of those things too, where it's like when I write code, I try to think about what the code's gonna do. I try to think about it before I actually do it. Right. The natural thing to do is typically just start brute forcing right in the code and see where it goes. Right. Generally, you want to kind of think about, oh, well, it would be easier if I did this. Again, some of that thinking is easy because I have experience, right, with it, but that's the kind of thinking that you guys want to start to do. Okay. What's that first if statement doing? Saying if n complex equals 0, what am I doing there? This is the DC term, right? So I'm basically taking whatever the alpha n value is there and multiplying by a series of ones. For any other values, I'm adding to the series basically what is implemented here. Alpha n times e to the j n omega naught t. And for me, basically I'm writing this and like I'm very variabilizing this, right? So I say alpha n of k, n complex of k. So in other words, I'm taking the n value that I am using, right? The n value that I'm using is being indexed through by this index k, right? I have an indexing variable that's going through those things. You might look at this and say, this is complicated for me, right? This, I think notionally, you guys should be able to understand what's going on here, right? You've done stuff similar to this before. All right. Maybe you haven't done it in MATLAB, but you've done similar stuff to it before. All right. So if I actually make all those things, what I did here was I plotted the original signal. This is the sine cosine. This is the shifted sine. Shifted sine or shifted cosine, sorry. This guy's the complex. Plotted all three of them or all four of them together. What I see is they basically are all sitting around on top of each other. It's a little bit of error there, I think. But basically they're all sitting on top, which they could, because they're all equal to each other. Right? They're all equal to each other. So they all sit on top of each other once I draw the graph, which I did over 4 periods. Looks like a lot more than 4 periods, but it's 4 fundamental periods. All right. So it's basically going from, if I look at this, that's small, -8 milliseconds to 8 milliseconds. Right. So 4 periods. Okay. All right. That is basically a lot of what's on the homework, basically the problems 2, 3, and 4. All right. Problem 2, I guess, is just you're dealing with a single sine wave. So a single, not a Fourier series. You're just dealing with, I have a single sine wave in this form. I need to get to the other 3 forms. That's basically what I'm asking you to do. Problems 3 and 4, you're doing this thing. Okay. All right. So it's one of those things that once you get into it, you haven't yet. It's not too bad, but the code may intimidate you guys a little bit. But the code is, if you follow what I did here, really the only thing you have to change is the n sub d, right? Just the number of harmonics is going to be different in those different cases, as well as the fundamental frequency. You'll need to change that, so you can change the values and things. But you more or less can follow my coding. Okay. All right. One thing about this DC term, it's confusing. The DC term in this waveform is 10. So if I look at this, right, in this form of the series, 10 equals A0 over 2. So A0 is 20. Okay. In this form of the series, C0 over 2 is equal to 10, or C0 equals 20. let's plug in n equal to 0 here. If I have it, so in other words, if I try to pattern match to this guy, if I plug in n equal to 0 in this form of the series, I have alpha 0 times e to the j 0 omega naught t. What's e to the j 0 anything? 1. This guy becomes alpha 0. What's alpha 0 equal to? 10. Right? A0, C0, both are 20. Alpha 0 is half of that. Right? Looks weird, right? Again, I probably wouldn't do the over 2. All right. They didn't have to, but that's the way they defined it. All right. And they didn't ask me my opinion on it. So that is what we got to deal with. The reason why is because the reason why is because there's it just gets confusing. That's just the way it is. All right. Is that, and again, you really want to know, we can talk about it, right? But basically that's a definition that we work with. Okay. So the way I think about this then is the DC term is always the average. So DC term meaning the frequency is 0. That n is 0. That DC term is always the average value of the waveform. The way I calculate the average is to integrate over a period and divide by the period. Okay. So alpha 0 equals A0 over 2 equals C0 over 2 is equal to the average value of the waveform over a period. And the way I write that is like this. So I can sometimes say 0 to capital T. What does it say? I can do it over any time period that encapsulates a period. All right. So from T minus capital T to capital T. Or I could say 0 to T. Or I could say negative T to 0. Right? Different ways of doing it. Okay. I just usually choose the one that makes the most sense. And notice there's never a B0 term. By definition, that is 0. Okay. All right. All right. So the question becomes, how do I figure out the coefficients for any periodic waveform? So the example we did when we started talking about this is I got a square wave. I said the square wave is this. I had a DC term, right? The average of that waveform. And then I had only sine waves. So somehow I needed to figure out that I didn't have any cosine waves. Okay. Also, when I look at this, the fundamental, what's the fundamental period here of this waveform? 1. Okay. So what's the fundamental frequency in radians per second? The period's 1 second. The fundamental frequency, omega naught, is 2 pi over what? 1. Or what? 2 pi. That's the first harmonic of this thing. Okay, that's the fundamental. What is this then? This is the fundamental, or what I call the first harmonic. What's this one here? Third, right? Because I'm multiplying that frequency by 3. All right, somehow this apparently doesn't have a second harmonic, or a fourth, or a sixth, or an eighth, right? How do I know that? Well, I know that because I know how to calculate what the coefficients are, right? So we got to figure out how do we calculate the coefficients. So I want to think this through for a second, right? So here, let's say I got this guy. All right, I want to figure out what the Fourier series coefficients are. All right, so this guy, what form of the series do I have here with what I've written here? Cosine plus sine version. Okay. So looking at this, 2 pi 1000 t, 4 pi 1000 t, this guy ends up being my fundamental. All right, that's my fundamental or first harmonic. Now, I can see that that's, well, it's probably not totally obvious to see that looking at the graph. I'm not going to try to, but that's the fundamental in this particular case, right? You can check that by checking the GCD, the greatest common divisor of those two things. If this is the fundamental, what's that guy? Second harmonic. How do you know it's the second? Divide, yeah, divide by the fundamental. So in other words, this frequency, 4 pi 1000 is twice 2 pi 1000. Right? That's the second harmonic. All right, now, in this case, do I have a DC term? No. And so if I look at this guy, I see he's sitting around 0. He's got no average. Okay. So I see that it has no DC term visually. I also, when I look at the equation, I see it has no constant. Right? So that means that A0 is 0. So A1, B1, A2, B2. What's the amplitude of the sine term at the fundamental? Fundamental is 1,000 hertz. What's the amplitude of the 1,000 hertz sine wave? 0. All right, that means that B1 is 0. What's A1? 3. What's A2? The amplitude of the cosine at the second harmonic? 0. What's the amplitude of the sine at the second harmonic? 2. All right, so now we know what those are. Let's say I wanted to figure those out. Let's say I didn't know them. Let's say what I did was I had an A to D converter and it was measuring this wave. That's what happens, right? So we do this a lot. So like, for instance, I could be concerned about the power quality in it. So the Duke is supposed to be giving me a nice little sine wave coming out at the power outlet, but maybe it's not. Maybe it looks like that. All right. If I want to figure out what harmonics are in there, I measure that waveform and then I do a set of calculations. All right. And then I figure out that I have these values. So how do I figure that out? Here's a way. This looks a lot like what I gave you in the project, right? So I gave you those communications things, right? So what I do is I took that original waveform, x of t, which has the sine and the cosine, right? This guy being the fundamental, this guy being the sine, the second harmonic. Now, what am I doing here? I got a multiplier block, all right? So multiplier block. So what happens here? What is supposed to be right here? What's coming out of that multiplier block? It would be x of t times cosine 2 pi 1000 t. Right? Makes sense? This is cosine 2 pi 1000 t. I multiply that by this. If I look at that waveform, it looks like this. Right here. Right? It looks like this. Now, looking at this guy looks like he goes from a little bit below 0, all right, all the way up to almost to 4. Right? Almost to 4. Right? So what I then do is I take the average over a period of that thing. So let's think about that for a second. If I do this multiplication, all right, if I do this multiplication, all right, x of t, so 3 cosine 2 pi 1000 t plus 2 sine 4 pi 1000 t. Right? I do that, and I multiply that by cosine 2 pi 1000 t. Okay. You had a problem like this in the project. If I do that, okay, and I go through that whole process, what's going to happen? If I multiply a cosine by a cosine, what that's going to end up becoming, if I go through this trig identities to figure this out, it's basically going to end up being 3/2 plus a cosine 2 pi 2000t plus some other cosines and sines, all right? Let's put it that way. I don't really care what they are. I'm gonna have a constant value plus a bunch of cosines and sines. Okay. What happens if I average a cosine over one period? What's the average value of cosine over a period? Zero. The average value of sine over a period. Zero. So what I do is I take this waveform here, this ugly looking guy, and I average over a period. If I take this thing that's basically a constant plus a bunch of cosines and sines, and I average over a period, what's that going to be? Constant. It's going to be 3/2 is what's going to come out of the averaging operation. I multiply that by 2, and it becomes the number 3. So what I did was I just came up with an approach that essentially implemented for me, figuring out that coefficient. I took the waveform, multiplied it by a cosine, averaged over a period, multiplied it by 2. Right? That's something I could, I could implement that with hardware. I could implement that in code. There is an equation that I'm basically going through here. I'm taking x of t, multiplying it by cosine at the fundamental. I'm then averaging over a period. What operation is that mathematically? What's that? It's integrating over a period and dividing it, right? So basically what I did here was this output right here, this guy is x of t times cosine omega naught t. This guy right here, coming out of here, is x of t cosine omega naught t dt times 1 over t. What's coming out here is 2 times that. So basically what I just derived for myself is that to figure out the A value, I derived it intuitively, right? To me, it's intuitive, probably a little bit more intuitive to me than it is to you. But basically what I'm saying is the act of multiplying x by this created a constant plus a bunch of stuff with 0 average. I took the average of that. It gave me essentially this amplitude, half of that. So I multiplied it by 2, right? So essentially this is the approach that I would use to make that calculation. For B of n, I do a similar thing, right? For B of n, instead of taking the waveform and multiplying by cosine, I multiply it by sine, okay? And so, intuitively, I can basically try to take the same approach here. So what I did here, what am I doing here? Right, well, I'm taking x of t and multiplying it by sine. That's what this guy looks like. Okay. What's the average of that waveform? Just looking at it. What's the average of this waveform? Looks like it goes from -3 to 3, and it keeps repeating. 0, right? Now, what is, this guy is calculating B1. B1 was 0, right? Because we didn't have a sine term at the fundamental, okay? What am I doing here? Calculating the second harmonic amplitude for the sine term. Right? If I look at the average of this guy, the average of this guy works out to be ultimately 2, if I calculate it, right? The average of this works out to be 1, and then I multiply by 2 to get 2. Right? And you could calculate that by using trig identities with these things. Right? You can prove that to yourself if you want to. That leaves us with these 2 equations. This is how I figure those out. So the thing is, anytime I have x of t times cosine, if I do that integral, right? You guys kind of learned when I have 2 functions multiplied like that, usually that leads to integration by parts, right? And integration by parts is ugly when I have cosine and sine. Why is that? Better remember.
Because now there goes a land.
You end up having to do the integrals twice, right? Until you can do it. And it's just ugly, right? So we don't like that. That's really kind of why we use this version of the series. I could prove this as well. I don't want to. It's weird, all right? Because it's got the complex stuff. So basically, I'm saying the complex form of the series, I figure out in a really similar way. I take the waveform, multiply it by e to the negative j n omega naught t, integrate over a period, and divide. Okay. All right, divide by t. This guy is the easiest way to do the calculus in general. All right, that guy is the easiest way to do the calculus. Now, let's say I had a square wave. This is the square. So I was basically saying what I said before is I said that A0 for this guy was equal to 2. And I said that all the other A values is equal to 0 for n not equal to 0. And I was saying the B sub n values were equal to 4 over n pi for n odd. Right, that's what I did when I did my little MATLAB example. I did that. Now I knew that because I knew how to calculate those things from those formulas, right? So if I have this waveform, it's got a period t. I want to be able to calculate those values, and in particular, easiest way for me to do it is to use the alpha n approach. So integrate over a period times e to the negative j n omega naught t dt. And we've got 4 minutes left, so I'm not going to have time to go through that. But basically, the process of this is pretty straightforward. It looks like it's pretty straightforward. Basically, what do I do? 5 steps that I've got, right? So first thing I do is I got to identify a suitable period over which to integrate, right? I just say a suitable period over which to integrate. I got to integrate over one period. Sometimes I do it from 0 to capital T. Sometimes I do it from negative t over 2 to t over 2, all right? Usually I just try to be smart about which way do I think the calculus is going to be easier. Sometimes the calculus is easier one way or the other. Doesn't matter. I just try to get the easiest calculus. Okay. Second thing is I got to figure out an equation for the function over the period that I'm integrating. All right. Then I got to figure out the alpha n coefficients for everything except n equal to 0. Then I figure out alpha 0, which is the DC term. Okay. Then I relate my alpha values to all the other forms of the series. The A, the B, the C, blah, blah. Okay. So let's think about this for a second. I will start this. I'll go to the second step. The period here should be obvious, right? What's the period? T. All right. This guy repeats the period T. So I made that part obvious. But the step 2, how would I define the function? So I'm going to integrate from 0 to capital T. Okay. I'm going to integrate over that time period. So I need to figure out what is the function x of t over that time period. How would I define that here? So it's 2 from 0 less than t to t over 2. And then I would say it's, 0 from t over 2 to t. That's the function I'm going to integrate over. Right? So I got to define what that function is. Then I can do the integrals. All right. Step 3 is then to do the integral. All right. So let's at least set that up. Right. What would that be? So alpha n is equal to, so x of t is equal to 2. Let me not set that up. We got 1 minute left. Right. X of t is that. That part should be easy. That part you should be able to think through. So when I look at that, though, we're doing the integral should be easy in this case. Do I have to integrate over both of those time periods? No, why don't I have to integrate over one of them? Which one do I not have to integrate over? The second one, right? Because x is 0. Right? 0 times anything is always 0. So integrating over that, there's no area under the curve from t over 2 to t. So there's nothing to integrate over. Okay. So this is what I've got. So ultimately it's not that hard. All right. We'll do the integral next time. And there's none of this stuff on the homework, right? This last part here, you don't have to deal with. The part that you have on the homework is basically everything that we had done up until now. All right. All right. I'll stop there.